Thank you.
It is.
Not good. So let's start the second session. The second speaker in the morning session is Jochen Koenigsmann from the rival of Cambridge, and the title is TBA.
Well, thank you very much, and thanks the organizers very much for inviting me to this wonderful conference and giving me the opportunity to say something. So the title has been around all the time. I'm afraid it's something is missing. So this is the full title. Now, if you want to fill it up completely, it says the Birational Anabelian section conjecture over Q. So I'm sorry I didn't give that title in full detail any earlier because I wasn't quite sure what I was going to talk about. Now, it's really only some elementary remarks about that. We've heard a lot about the section conjecture with very highbrow techniques, and I will only use elementary things and make some remarks about that. So my talk has two parts. I start with an introduction, and well,
Do you use the word elementary in the logic sense, or?
it will appear in both senses. It will appear in both senses, yes. But not too much logic, so for all those who are afraid of that. Well, luckily, the first part will be very short because Jakob was giving yesterday such a nice introduction to the section conjecture that I can. Sorry?
Hey.
I have read it somewhere wrong.
Everybody does it.
I checked it, so I thought I should have asked. Anyway, so we have all now learned something new as well. So first part is very short because we've already had that. Now, second part, I will talk on fields with the absolute Galois group of Q. That is fields where there's an isomorphism of profinite groups between the absolute Galois group of K and the absolute Galois group of Q. Now, there is a conjecture here, and the conjecture says that this condition implies that the field is very much like Q, namely that K is either Q or, more generally, K has a Henselian valuation, call it V, with residue field, which I denote by KV, equals to Q, and with value group, which I denote by gamma V, divisible. So the two main examples here are Q, for which we know the absolute Galois group is the absolute Galois group of Q, and the Henselian valuation here is just the trivial valuation, or essentially the field looks something like the Laurent, the Puiseux series field over Q with exponents in some, for example, in the rationals. So, in fact, if I put this here, then this is the same thing. So, if the conjecture is true, then either K is Q, or there is a non-trivial Henselian valuation with divisible value group and residue field exactly Q. So this is the conjecture, and obviously this conjecture implies the birational Anabelian section conjecture for curves over Q. So it's a bit stronger than that conjecture. So I will make some elementary remarks about this condition and what follows from it, and I'm afraid I'm not able to prove this conjecture today, but I very much believe in it, in this conjecture.
Did you say that's elementary equivalence?
Yes. Yes.
Were you saying that any field that has such a Henselian valuation
is elementarily equivalent to this field? That is back to the theorem of Kochen and Yershov. That's a theorem from model theory. So this equality sign with 3 strokes means elementary equivalence. That means the same first order sentences are true. That means essentially that fields with this Galois group have 2 kinds of theories, either the theory of Q or the theory of this field.
Is that in the language with the valuation or just as field?
Just as fields. But you can always define the valuation.
And Q is not.
So it doesn't make a difference.
And Q is different, or no? Q is also.
Here, Q is the constant.
No, but Q is also linear. Is also elementary equivalent to this.
No, no. Those 2 are different. For example,
So
this field. Sorry.
Okay, so then you could also have anything.
No, they are. I mean, this is the only, according to this conjecture, the only distinction between 2 fields with that property. Either it is Q or it's something like this. For example, in this field, every variety with 1 rational point or every curve with 1 rational point has infinitely many rational points. That doesn't hold in Q. And it's an elementary property. But that is the essential property which distinguishes those 2 cases. So according to this conjecture, there are just 2 theories around here. Okay, now let me say what one can say here. First, local structure.
Can I ask one?
Yes?
So I guess the converse is not true. If you start with something that's elementary equivalent to that, then it might not have the same Galois group.
It might be larger.
Bigger.
Yeah, it might be larger. Yes, yes. But of course, every field of this shape has the Galois group of Q.
Okay.
Yeah, I mean all fields. I mean here, of course, you have the converse almost trivially.
But I didn't quite understand this implication. That this obviously implies the birational.
Oh, that is because I'll come to that in the course of the talk. Yeah, yeah, that is easy. Okay, local structure. First of all, we know by the isomorphism between. So we are now all the time assuming GK is GQ. There's an isomorphism between those 2 groups. Now, first of all, the absolute Galois group of Q is generated by the absolute Galois groups of the p-adic closures of Q. So that means also the corresponding isomorphic copies of the Galois group of some algebraic closure in GK, I denote by GKP, they generate. The group P is the set of primes, and in fact, we know that these fields KP, they are all p-adically closed. I can write it like this, elementarily equivalent to QP. That means they are all Henselian valued fields with residue field FP, value group, a group which looks very much like Z. I will say that more precisely. We have that for all primes, P, there is a unique p-adic valuation, say Vp on K, whereby p-adic I simply mean that the residue field is equal to Fp, that the value group is some divisible group, delta P, so this is a divisible ordered abelian group, with a lexicographic direct sum of a copy of Z, where the value of P is the smallest positive element. So it's 1, or if you wish, 0 plus 1. That is what I mean by p-adic. That follows immediately from this theorem that every field with a Galois group of QP is elementarily equivalent, is a p-adically closed field, which means a Henselian valued field with exactly this property down here. That was something Neukirch has already proved in some cases. Pop has generalized it, and I did the full thing in 1995. So we have this local structure here, and also it is true that these fields, Kp, are actually the Henselizations. So this is of course, up to conjugation, so I should better say a Henselization of K together with this p-adic valuation. So this is the p-adic local consequence. We have there all those Kp's and all the p-adic valuations. Of course, the Galois group of Q has also, up to conjugation, a unique involution, meaning that the same is true about GK, which means there is a unique ordering. So K has a unique ordering, and it is also true and seen from the Galois group that the positive elements are just the sums of 4 squares. So that is the real thing here. Now also, I mean, these Galois groups.
By the condition A, at least the K is over characteristic 0.
Yes, that falls automatically, yes.
And then we have the natural map to Q to K, natural embedding from Q to K.
Yes.
So we have a natural map from GK to GQ.
I will talk about that. Number 3. Thank you. Yes. No, fine. Third property, which I could also have mentioned up here, the Galois group sees all the ramifications. So that means for all finite extensions L over K, first of all, this is only ramified at finitely many places. Again, that is something the Galois group sees. And in fact, the Galois group sees much more, sees all local ramification indices, inertia degrees, etc. So the Galois group sees all the local things. So in particular, we have a Cherevatarief density theorem holding 4K with respect to this set of valuations, and that is very helpful. Now, the fourth thing, which is immediate from this, is that the Galois group sees all local global principles which refer to Galois theoretic properties. So,
how do you see Tsebotamev?
sorry?
Why Tsebotamev going to ramification?
So, for example, I know that when I have a finite extension, say a finite Galois extension, and an element sigma in the Galois group, then GK sees that at the correct density, many primes, I get a map where this is the Frobenius. Just because the ramification data are completely fixed. Just take the compositum of L with each of these KPs. There I can read off what happens, and because over Q things happen according to Cherevatarief, so they do over K. So that is
Density in this general situation.
Sorry?
How do we find density?
Oh, just density in the set of primes. I mean, I'm just here talking about sets of primes, and I'm only referring to those p-adic valuations. Yeah, there's nothing deep here. Yeah.
You're just saying that we can see from the decomposition group which ones are split.
Sorry? We can see from the...
You can see, for example, which ones are split.
We can exactly see which ones are split. We can exactly see which ones ramified. All that is just encoded in the Galois group of that field. Now, and then, as I was saying, all local global principles for, say, Galois properties. I mean, properties seen by the Galois group hold, of course, only those which hold in Q. So, for example, we have that an element X is a pth power or an nth power in our field K, if and only if it is so everywhere locally. So for all p, including the infinite prime here, we have that x is an nth power in Kp, where of course the completion K infinity is just the real closure. Or we have, for example, the Hasse principle for quadratic forms. For the representation of quadratic forms. So an element in K is represented by a given quadratic form over K if and only if it is so everywhere locally. Again, that is something which by an easy induction argument you can show from Galois. That is something the Galois group sees. What else do we have? I mean, there are many interesting things, but perhaps I'll use some of them in the course of the talk, and we will see what other interesting. Well, one other interesting Galois theoretic property I should mention here is quadratic reciprocity. The quadratic reciprocity law holds over K in the sense that if you take for any two non-zero elements AB, the quaternion algebra AB and the Hilbert symbol locally at every P, where P is now a prime or infinite, then the product over that is equal to 1. That is a version of the quadratic reciprocity law. And again, that is of course something Galois sees, because these things live in H2 GK. So all these things are true in K as well. Now, so
you also have class field theory?
Yeah. You also have class field theory, everything. I mean, everything Galois sees. And yes, class field theory is very much something Galois sees. Now, secondly, let's move on to what you may call global integers. Now, it's clear how to define them. I define them to be the intersection of these valuation rings. Now, that is obviously a subring of K containing the integers. We don't know how big it is yet, but we will say something about that sort of later on. Now, first simple observation is that if you have a unit in this ring of integers, what I call it, but of course you have to understand that correctly. It's just the intersection of these valuation rings. So obviously a unit here is just the intersection of all the local units. And I claim that this is a global 1 unit or minus a global 1 unit. That means those things are plus or minus 1 plus something which is in the intersection of all the maximal ideals of these valuations. So let me prove that. That is rather easy, because suppose you have a global unit, then I can assume that it is greater 0, otherwise I just multiply it by minus 1. We have only one ordering here, so with respect to that ordering, I may assume it's greater than 0. But now, suppose it is somewhere x is not a 1 unit at some prime p. Obviously, that has to be then an odd prime. Well, then I consider the element 1 I consider, yes, if it's not a 1 unit, then obviously the element x is not a square. I may assume that, because if it's somewhere locally is not a 1 unit, then you can locally, in the residue modulo fp, take squares only so many times. So it may be a 2 to the nth power for some n, but certainly not a 2 to the n plus first power. So you take the first n where that happens. and take, of course, if you take the square root of x, it's again a global unit. So let's, without lack of generality, assume that it is not a square. On the other hand, it's a unit everywhere locally, also at our prime at infinity. But that means that because every quadratic extension ramifies somewhere, there's only one place where that can ramifies exactly and only at the prime p equals 2. Ramifies only at 2. But that means that x is, well, if I say now congruent 3 or 7 mod 8, I should be careful because I'm not talking about rational numbers here. What I mean here is mod the duadic valuation ring of V2. So, but then we have that the quaternion algebra x comma x is duadically non-trivial. So the Hilbert symbol here is non-trivial. But by the product formula, that means it has to be non-trivial at some other prime. So that means, because it's obviously trivial over the infinite prime, there must be one other prime, so that must be an odd one. For some odd p, but that can only happen for odd p's when the value of x is itself odd. But that means then that the p-adic value at that prime is odd, which is a contradiction because we have chosen x to be a universal unit. So that proves this little observation here. Now the second little observation is that if you take something in this intersection of all the local maximal ideals, then that is in fact already something which lies in this intersection of all the finite powers of these maximal ideals. Why is that? Well, suppose you have a global element in the maximal ideal, which, however, is not, say, in q to the n times the q-adic maximal ideal for some q, and n.
So this formula is the last formula.
Sorry?
So it means that not only for the fact that the chiral groups are the same, you conclude that the two torsion part of the chiral group is in mod 2, but also the identification with the Z mod 2 is the same. It's given by
Yes.
the
Yeah.
same computations of residues.
Yes. 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 Same thing. Yes. Of course, I mean, this Galois group sees a lot more. It sees all the cyclotomic extensions. It sees a lot, but we don't need that at this point here. So why is it that every global maximal ideal element is already here? Suppose this were not true, then for some n and q we have something in here which is not in there, but then we have locally that 1 plus x is a 1 unit, of course, everywhere. But that means, by Hensel's lemma, that it is locally a q to the nth power for every p different from q. But then it must be a global q to the nth power. However, q-adically, you easily see that it is not. Because when you take this 1 unit, q-adically take a q through it, then the value of x has to go down a couple of times. It can only go down so many times. So for some n, this doesn't work. So this cannot work, and that proves that indeed this maximal ideal is already that maximal ideal, which I may write also as the intersection over all P in P of the maximal ideals of Vp tilde, where Vp tilde is something I should have introduced here. I said that all those p-adic valuations have this divisible part in the value group together with the lexicographic part. That means in particular that if I define the valuation Vp tilde to be the coarsening of Vp with the property that the valuation ring of Vp tilde is just the valuation ring of Vp together with, just adjoining p to the minus 1, then that means that in the value group I kill that part here and I have value group. So here that gives me that the value group of V tilde, this relative rank 1 coarsening of Vp, is just the delta P we had over here. So sorry, that is something I should have said before and something I will be referring to a lot in what is to follow. And using this, I can rephrase that thing here simply by saying that this is the intersection of these things. In particular, we have that as a corollary. We have that the intersection of all maximal ideals is trivial, and of course using part A, that means that the only units in our ring of integers are plus and minus 1. In the following two cases, if, well, either there is one rank 1 valuation Vp, that means a valuation Vp where the value group is just Z, where this delta is 0, delta P is 0. Sorry?
OK star. OK.
Thank you. So that means just gamma Vp is the 0 group, or equivalently delta P, gamma Vp is Z, or equivalently delta Vp, delta P is the 0 group. So in that case, because obviously the intersection of all the q to the n powers of the maximal ideal then is 0. Or there's another case where that happens, and that will be interesting later on. If the transcendence degree of k over q is just 1, and it so happens that the Vp valuations induce on some function field over q, which is inside k, infinitely many places. So that means this is 1, and if I take those Vp tildes and restrict them to some f where f over q is a function field, some function field or every function field amounts to the same thing, with which lies in k if there are infinite, and there are infinitely many such places. Because then the intersection of these places, which are infinitely many, again is 0. That will be important later. Now, let me come to Akiu's question. It happens that the restriction map from the absolute Galois group to the Galois group of K, that is in fact under the assumption that there is an isomorphism between GK and GQ, then this is also an isomorphism. Of course, that may not have been the isomorphism we started off with, but it will automatically be. And the reason is quite simple. First of all, the second condition is that the transcendence degree of K over Q is 1, and there are infinitely many distinct. Yes, I guess that's that means the Vp tildes, when you restrict them to some finally generated subfield of K over Q, which is transcendental, there will be infinitely many topologies, or that will be infinitely many places. That may or may not happen. So we will come to the case where it does happen and to cases where it does not happen. Okay, why is it the restriction map an isomorphism? Well, that is simply, well, it is onto because the GKPs, the subgroup of GKP which generate GK, they map onto G, say, QP alg for some, I'm not saying all here, but for some choice of p-adic cancelizations of Q, but then the intersection of all of them, no matter how you've chosen them, is just Q. So that means K intersect Q tilde is just Q, and so it's onto. Now, moreover, there's an important thing. We know by the Galois group, knowing everything about ramification, that every finite extension is only finitely ramified. And indeed, to a given degree, there are only finitely many extensions ramifying at finitely many primes. So let K upper n be the compositum of all Galois extensions L over K of degree at most n and ramifying at most at primes P which are less than or equal to n, and that is a finite Galois extension of K. And in fact, this Galois extension is the compositum of the corresponding field extension over Q, because those finitely many ramified things come from locally from the corresponding ramified thing. So this is exactly the compositum of K with those maximal unramified outside primes less than n, maximal degree n extensions. So that means that if I take the union of these Kn's, then that of course is K bar, the algebraic closure of K, because as he said, the Galois group knows that every finite extension is only finitely ramified, so they occur somewhere. And because that is the union over all n's of K Q to the n, that tells you that this field is KQ bar, which gives you injectivity of the restriction map. So no matter how we have chosen our isomorphism to begin with, we might as well take this one. So that is a simple observation. Now, let me come now to a case which we can manage, namely the case which I will call the semi-local case. The semi-local case, now, and from now on, I will have the assumption that the transcendence degree of K over Q is 1. So that means, having done this restriction here, we are now actually talking about the birational Anabelian section conjecture for curves over Q. Now, the semi-local case here is that for each, for some, and that is the same as to say for each. I mean, I'm not saying that some is each, but you'll see. Function field F over Q inside K if I
the last one.
Thank you. The restrictions of all my VPs, which are valuations on K, down to F, induce finitely many topologies only. All these things induce finitely many topologies. So if, for example, you take this case here, I mean, the relative algebraic closure of Q of 2 inside here, then this is such a situation because it's just the t-adic topology which is common to all the p-adic valuations living on that field. So that case does occur. It's not the empty set I'm talking about here. Okay, now if that happens, then let's say W1 to Wm be all non-trivial valuations which are of the shape Vp tilde, so this relative rank 1 coarsening of the Vps intersected down to F. There are only finitely many by assumptions. I mean, of course, they are rank 1 valuations. They all induce different topologies, so there can only be finitely many. By the way, I didn't explain why sum and each is the same here, but I mean, if you have some function field where there are only finitely many topologies around, then if you take a finite extension, there are still only finitely many around. So if you take any other function field, take the compositum, same is true. So that is why sum is each here. So suppose we have all these non-trivial geometric places here, which are induced from VPs, and then of course there may be non-geometric ones. There may be rank 1 extensions of the p-adic valuation on Q to our field. There are many ways to do that. So call them Wn plus 1 up to Wn. And of course there should again only be finitely many because they are rank 1 and they are all induce different topologies. So we all rank 1 restrictions of Vp to F. Then the first thing I want to show is in that case, in fact, M equals N equals 1. There's no other possibility. So let me show that. Now, there is a simple observation that. Sorry?
Do you want to say that let F over Q be such that?
Let F be some such. Yes.
That means, but we do not know that for K there is such an F, but suppose that there is.
Suppose this is the case.
Okay.
The semi-local case is the case where for some, that means each function field, we have only finitely many topologies around. I will show in that case there is a Henselian valuation on K with divisible value group, and the conclusion of the conjecture holds. But the first step in the proof is to show, well, then there is only one topology around. And then I will have to continue. So why?
When you speak topology, it's always topology defined by Vp tilde.
Here it's the topology. Oops. I'm sorry. This tilde was wrong. Here I talk about the Vp tildes, which are non-trivial. That means here the Vps have not value group Z, but value group Q plus Z. Whereas down here I look at those Vps which are of rank 1. That means where the value group is actually the integers. And as I was saying, sorry, this tilde was wrong here. Thank you. And I was saying because those are all now rank 1 valuations, they all induce different topologies, so there can only be finitely many under this assumption.
But what was the difference between V to V, the tilde V and the primary V?
The tilde V, tilde Vp, is the valuation Vp coarsened by taking in the valuation ring inverses of P. That is a relative rank 1 coarsening, and that has divisible value group. And sometimes this divisible value group is trivial and sometimes not. So here I'm taking those where it is not trivial, and then because we have transcendence degree 1, it's a rank 1. That means the value group is in fact Q in K. I'm not saying about F, but in K the value group is Q. In F, of course, it's Z in some version or another.
Okay, so is it true that your hypothesis here is take all the p's for which VP tilde is trivial?
Yes,
There are only finitely many such.
that's the ones here.
Second, now take all the p for which VP tilde is non-trivial and look at the VP tilde.
Yes.
They should be also only finitely many.
Exactly. That's exactly the case distinction. Yes. Sorry if that seems unnatural, but that's how the proof proceeds. Why? No? Okay. Why is this true? Well, there's a simple observation that if you have non-zero sets of non-empty sets of primes, say sigma 1, sigma 2, sets of primes such that they are disjoint and the union of them is cofinite in P, then there are elements Li in sigma I such that L1 is a quadratic non-residue modulo L2, and one of them is concurrent 1 mod 8. Maybe both, but at least one is concurrent 1 mod 8. That's a trivial observation which we now use for the following set, sigma 1. Sigma 1, we want to be those primes which have the property that their VP tilde intersected to F is actually W1. Now I should mention here that in fact M must be greater or equal to 1. There must be some valuation which is not of rank 1, because if all valuations were of rank 1, then of course all the restrictions would be of rank 1. I would have infinitely many topologies. So I certainly have some guys up here. I'm not sure about those down there. In fact, as part A shows, there are none, but a priori there might be. So let sigma 1 be the set of primes. And then choose L1 and L2 as above. And without lack of generality, I may assume that my L1 is in fact concurrent 1 mod 8. Now, so I let, of course, sigma 2 be the complement of P with sigma 1. Now, this observation here only gives me that either L1 or L2 is concurrent 1 mod 8. So there may be none in sigma 1. However, there are only finitely many valuations of this sort, so only finitely many primes occurring here. That means apart from these finitely many primes, I can decompose the set of primes occurring here into disjoint ones, namely ones coming from W1s and the other ones coming from, say, W2. So if it happens that my the prime Li, which is concurrent 1 mod 8, was in fact L2, then it's in this set here, but then I pass to W2. So, I mean, without lack of generality, then just relabeling these things, I may assume that the one which is concurrent 1 mod 8 is actually one lying above W1. So, and then, of course, I can use a strong approximation. I choose an element X, which is in L1 plus M W1, but is, with respect to the other finitely many topologies, a 1 unit. So is the intersection for I greater than 1 of 1 plus, well, and to be sure, I make it in 1 plus 8 times the maximal ideal of Wi. So I'm doing a proof by contradiction. I suppose here that sigma 2 is non-empty. I want to lead this to a contradiction. So that means there are actually elements in here. Okay, if I choose such a thing, which I may, of course, by strong approximation, those are finally many rank 1 valuations, then I can I observe that obviously x is not a square, and because at the prime L1, if I join square root of x, I will have square root of L1 in the corresponding local field. So if I join square root of x to k, then where does that extension ramify? It certainly ramifies at L1, but it doesn't ramify at any other, because it's a unit in all the other things here, and because I have chosen L1 congruent 1 mod 8, even if 2 occurs here, it will still be a duadic square, so it will be here because I've put the 8 in here, so there's, suffices to put 4 actually. It will be a duadic square. That means this extension is the unique quadratic extension of K ramifying only at L1. But this extension, because I've chosen L1 in such a way that L1 is a quadratic non-residue modulo L2, this should give a quadratic extension of K L2. However, L2 is in this set, and here I have 1 units all the way, so, or 1 plus 4 units if the prime 2 occurs here. So they are all squares locally, so that is a contradiction. So that cannot happen, and therefore the set sigma 2 must have been the trivial set that means all primes lie above W1, and that means then that there is a unique such thing that means m equals n equals 1. So now let V be Vp infinity for, again, sum equals each P in P. Because, I mean, I've taken an arbitrary f here of this sort. Every arbitrary f has just one geometric prime where all the VPs are centered, so to speak. And they, of course, lift up to a unique valuation in K. So I call that V, and now in part B, I would like to show that V is Henselian on K with residue field equal to Q and value group also equal to Q. Two very different kinds of Q, though, but anyway.
I'm sorry that I have been confused, but this case is, I know this case is not you defined the semi-local case, but
yeah.
This is VP tilde, right?
Here
third right. Yes, that's third right. So yes, VP tilde, right? Not the VP.
Oh, VP and VP tilde induce the same topology unless VP tilde is trivial. If you have a coarsening of two valuations which are both non-trivial, they induce the same topology. So yes, I here just assume that the VPs induce different, finitely many topologies on each finite.
This kind of phenomenon really occur. So the semi-local case
really exists.
Yes, for example, I will show you one. I mean, I've already said it. If you take, oops, it's gone. If you take, e.g., the intersection of the algebraic closure of T with Q double T, Q double Q.
I think that
That is an example.
what you really want to say in A is that n is 0.
No, n equals n. That means these guys don't occur. So it's 1 to m, m plus 1 to n.
There is a problem because if m is 1, then m plus 1 is 2.
Yeah, so there is none. It means there is none.
Yes, so there is none. But maybe I should just say n equals 1. That's good enough. That tells us that there are no guys here. Yes. Anyway, sorry, it's time's coming.
M equals 1.
No, m could be 0.
M equals
That was
M is 0, then there is an n.
m equals 0.
Then there is
M
an-
equals anyway. What I want to say is these guys are not there. And, let me say why this valuation is Henselian. Well, that is a simple argument which refers to the things I've done here, namely for each finite extension of K that lies in some Kn. Well, first thing which is clear is that that we said already here, that the value group, of course, is just Q. It has to be divisible, and it's rank 1, so it has to be Q. Now, also, we have that if I consider those Kn's I introduced over there, which are K adjoined the corresponding Qn's, then these are things which are yes, these are things where the valuation, no, sorry. I first say why the residue field is Q. Excuse me. The residue field is Q because these VP tildes are at each KP, at each of these Henselizations here. The VP tildes are the relative rank 1 coarsenings of the VPs with value group Q. So they have here residue field, the algebraic extension of Q, which is a periodically closed field. So at each, this V has residue field at each of these things, which is a QP alk. So what we have is that the residue field is an algebraic extension of Q, obviously, which is contained in the intersection of QP alks for all primes P. Some choice here, but anyway, and this intersection, of course, is Q. So that is why the residue field has to be Q. Now, why is the valuation Henselian? It's Henselian because now take k to the n, which we observed is the same as k q to the n. This is this maximal only at primes less or equal to n ramified compositum of Galois extensions of degree at most. And that is, in fact, a purely inert extension because the residue field will just be this Qn. It's purely inert extension of k with respect to this valuation. Therefore, the valuation has a unique extension to this field. And this is true for every n, but those kn exhaust the algebraic closure. That means V has a unique extension to the algebraic closure, which is the same as saying that it's Henselian. Okay, now that finishes the semi-local case. That means in the semi-local case, only the things we expect to happen, namely the field K has a Henselian valuation which has residue field Q and value group also Q. So the semi-local case is dealt with. Now the difficult case will be the non-semi-local case, and I will come to that. Now, the non-semi-local case, the key problem is to see whether there are elements which are in the maximal ideal of infinitely many primes. So what was the numbering 5 is now the non-semi-local case. That is on each function field f over k. Again, here I'm working with the case transcendent degree k over q is equal to 1. Now, in this case, by the corollary I was, I think, just erasing, we know that the only units are plus and minus 1, the only global units, and the intersection of all maximal ideals is 0. So in this case, we have that the intersection of all the maximal ideals is 0, and the only global units are plus minus 1. That is by the corollary I had in part 2. Now, what I want to show is that for each non-zero element, the set sigma x of primes where the p-adic value of x is greater than 0, that this set, well, one thing I can show here is has Dirichlet density 0. Now, why is that? Take such an element x in k times, of course, outside Q, because obviously for the rationals this is always true. So a non-constant element in my infinite function field k over Q, and what we know is that sigma x is certainly different from all the primes, because we said that things which are in all maximal ideals are just the 0, and I was taking a non-zero element. So I choose a prime, say Q, outside sigma x. So this is certainly a prime where the value of x is less than or equal to 0. So then I consider the element 1 plus x squared q to the minus 1. This certainly is a 1 unit at every prime from sigma x, because q is outside sigma x, so if I divide by it, of course that doesn't change anything. But also this is an element which q-adically has an odd value, because I mean, either x was a q-adic unit, and then the value of this guy is minus 1, and then so is that, or it was a q-adic non-integer, but then it has a negative two-fold value, and then if I divide q to the minus 1, it has a negative odd value, and of course that is the sum here, the value is dominated by that. So this is obviously a non-square, and therefore, I mean, in the extension k adjoint a square root of 1 plus x squared q to the minus 1, which is a proper quadratic extension, all the primes from sigma x, in all the primes of sigma x, nothing happens, because it's a 1 unit. Or maybe for p equals 2, but I don't care, because I'm interested in finite or not finite here or size of things. So anyway, that tells me that the density of the primes in sigma x must be less than or equal to 1/2 by Chebotarev. And then I go on. Then I pick a prime, say L, which is not in sigma x, but which is also not in the finitely many. I mean, this extension here, of course, it has to be an extension of the shape k adjoint the square root of some product of finitely many primes, q1 up to qr, where certainly this q is one of those. But anyway, there are only finitely many. So I can now choose a prime which is away from these finitely many and also not in sigma x. Of course, that exists because now my sigma x has density at most 1/2. So then I can consider the corresponding thing, the element 1 plus x squared L to the minus 1. That means that this is another quadratic extension that is not in here. So that means, again, because all the primes in sigma x, nothing happens there. It means that now my delta of sigma x is less than or equal to 1/4, etc. So that means that delta x is equal to 0. Now, sorry, I'm running out of time. The sad thing is, I cannot show at this point that this set is in fact finite. I very strongly believe that it is, but this is still open. Let me just finish by explaining what happens if this is indeed finite. I mean, these are very, very strange sets here, these sigma x's. I mean, they are sets which have to obey infinitely many arithmetic progressions, and you have some choice, but also not too much, because you don't know exactly which Q1 to QRs occur here. So it's a tricky thing, but I hope playing around with that, using a bit of reciprocity and other things, that one will be able to show the following hope for all x in k times sigma x is finite. Now, the hope implies the conjecture. Let me briefly indicate that. Well, that is simply because pick any element x which the conjecture that the non-semilocal case doesn't occur. So maybe I should say the hope implies that the non-semi-local case does not occur, and then the only case we are left with is the one which we hope for. So let me just indicate briefly why that is. Sorry, 1 minute. So pick a non-rational element in K, and then of course you can consider Q of x. Now I construct extensions, F1, F2, etc. Infinitely many extensions, all lying in our field K, in such a way that those are all genus zero fields, namely I adjoin to Q of x a say n factorial root of of x to begin with, but the problem is that might not lie in K. However, if there are only finitely many primes, then I can work at them. So I find some rational number Rn such that Rn times x lies in K to the n factorial. So I choose those R's correspondingly. So this is again by the local knowledge of the Galois group of K. So for some rational Q, I can do this in such a way that they really are in here. So they are all genus zero extensions of Q of x, inside K, and there are infinitely many of them. And then a little calculation shows that then it happens that there is a place W of Q of X, which has enough distinct extensions to some of these Fn's so that not all of them come from K. So there is a place W of K, and such that there are there's an N and extensions W1 and W2 of W to this field Fn with a property that W1 and W2 are not induced by any VP tilde. That is possible. The little calculation shows that. And then once you have that, you can choose in an element T in Fn, which is a unit at all places except at the W1 and W2. In rational functional field, that is always possible. So choose which is a unit at all, but not in Q, which is a unit at all places of Fn except at W1, W2. But that means that T lies in what I call O tilde, which is just the intersection of the O VP tildes here, P in P, and that shows then that because I have this hope that, and I'm assuming it here, that every element has only finitely many things, so it's only in the maximal ideal of finitely many. It's certainly now, by the construction, not in the maximal ideal of any V tilde. That means it's only at some maximal ideals for the P parts, for the VP parts, but then it means that for some primes, P1, so the element T times the product of those finitely many P's which are in sigma T of P to the minus D of T. I mean, this is obviously a rational number here because we're assuming this is finite. This is then a global unit in OK, but obviously it's a non-rational number, but our global units only were plus or minus 1, so that finishes the proof here. So the hope is to actually show this, and then one would have the birational section conjecture for curves over the rationals. I'm completely convinced, but I just didn't have the time to check so far. I mean, this is only 2 days old. That, and that's why the title did not come so early. The same can be done over number fields in place of Q. It's a bit more complicated. You need a bit more Iwasawa theory, but I think that is not the big issue. And if that hope is true here, you can, by an inductive step or by a relative version, in fact, go on to finite transcendence degree over Q, and then you have, in fact, the full conjecture for all. So it is this hope which one needs to check in order to prove the birational. Well, this big conjecture I have erased now, that any field with a Galois group of Q has a Henselian evaluation with residue field Q and divisible value group. Sorry for going over time.
So, questions or comments? So it's okay. So if you don't, let's discuss after the last session.